This is the ELEC 1510 Logic Design Lecture 1 Video 2 on number-based conversions. This video corresponds to the textbook section 1.4. First, we're going to talk about conversion from binary to decimal. This was already included in the last lecture, but I figured that I would include it here just for review. For example, let's say that we have a binary number 11011. The 2 subscript denotes that it's a binary number. It's base 2. This means that we have 1 times 2 to the 4th power. That is this one, which is in the 4ths place, plus 1 times 2 to the 3rd power. That's that one, plus 1 times 2 to the 1 power, plus 1 times 2 to the 0 power. Since there was a 0 in the seconds place, we don't have 1 times 2 squared. So that's going to equal 16 plus 8 plus 2 plus 1, which is 27 base 10. So conversion from binary to decimal is pretty easy. Whenever you have a 1 in a certain place, that's just 1 times 2 to the place of wherever that 1 was. Then you just add up all of those numbers, and then you get the decimal equivalent. Converting from decimal to binary is less straightforward. What you have to do is take your decimal number and divide it by 2 repeatedly and save the remainder each time until you eventually get to 0. So for example, let's convert 45 base 10 into binary. So first, we start out with the number 45. When we divide it by 2, we get to 22 with a remainder of 1. Now, once again, we divide that by 2 to get 11 with remainder 0. Divide by 2 again to get 5 with remainder 1. Divide by 2 again to get 2 with remainder 1. Divide by 2 to get 1 with remainder 0. And then finally, divide by 2 to get 0 with remainder 1. So eventually you need to get to a 0 here. And then you know that you're finished. Now, this is actually our binary number, where the most significant place is down at the bottom. The least significant place is up here at the top. So if we just sort of flip this and then rewrite it, we will get 10110 base 2, which is equivalent to 45 base 10. Okay, so we had covered octal and hex numbers in the previous lecture video. One thing that is done fairly commonly is conversion between binary and octal and hex. So we'll cover binary to octal first. Basically, how this works is that 3 binary digits, or bits, so whenever you hear about a certain bits, like, the 64-bit computer, that means binary digit. 3 binary digits can represent 0 through 7. So the first being 000, which is equal to 0, and the last being 111, which is 7. So then you have everything in between, like 010 is 2, 011 is 3, 110 is 6, etc. And we know from talking about octal number systems that in octal, each digit represents 0 through 7. So that basically means that there's an equivalency between 3 bits in binary and a single digit in octal. So what you do to convert binary to octal is just group 3 bits together over and over and convert those to one octal digit. So for example, we can take a really long binary number like 101001011011010 base 2, which is a pretty big number, and just convert that pretty easily into octal by grouping together groups of 3 bits. So we have a group of 3 bits here, 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 and here. Now conveniently I made it divide evenly into 5 groups of 3 bits. If it didn't divide evenly, then you would just add some zeros at the beginning to make it, to add an extra group of 3 bits. So those are a 5, a 1, a 3, a 3, and a 2. So 101 is 5, 001 is 1, 011 is 3, 011 is 3, and 010 is 2. So in octal, that converts to 51,332 base 8. To convert octal to binary, each octal digit just represents 3 binary bits, so you're going to work that process backwards. So for example, we can take a pretty long octal number, 354,176 base 8, and convert that into binary by just realizing that each octal digit represents 3 bits. So the very first one here, 3, is 011 in binary, 5 is 101, 4 is 100, 1 is 001, 7 is 111, and 6 is 110. So that's the conversion method into binary. Just so that you have a slide with all of these conversions on it that you can write down and try to memorize, here they all are. This is the type of thing that you should basically know right off the top of your head for this class, for the remainder of this class. All of these conversions. All right, so converting binary to hex is very similar. 4 binary digits or bits can represent the values 0 through 15. So for example, 0000, 4 bits is 0, and 1111 converted into decimal is 15. In hex, each digit represents 0 through 15. And that was 0 through 9 and then A through F. So groups of 4 bits in binary are just equal to 1 hex digit. So instead of grouping them by 3 to get to an octal number, we group them by 4 to get to a hex digit. So for example, let's take the number 1101, 0010, 1101, 1010, base 2, and group that into groups of 4 bits. So the first one is 1010, then 1101, then 0010, then 1101. And that comes out to be D2DA base 16. 1101 is 13 or D, 0010 is 2, 1101 again is 13 or D, and 1010 is 10 or A. Converting hex to binary, you just perform the exact same operation but backwards. Each hex digit is going to represent 4 binary bits. So let's take another hex number that looks like a word, food or F00D base 16. And we're going to just convert each hex digit into 4 bits. So F becomes 1111, 0 becomes 0000, 0 again becomes 0000, and D becomes 13 or 1101 base 2. So conversion between binary and hex or octal is very easy. It's just you have to remember these conversions between the bits and the hex or octal symbols.